Today we'll talk about topology optimization for a better design, which is the subject of today's webinar. So it's a really interesting subject, and I hope you will learn a lot on the way to improve your design using FEA simulation and optimization techniques. So today we'll talk about all these subjects. So first of all, what is adequate design and optimum design? What is the difference? What do I call an optimum design driven process? And what are the optimization types? The topology optimization as well will be the main subject, of course. So it will be in the fourth part that I will explain the theory about that. Then we'll talk about some concrete examples. So I'll make this first a simple tutorial with a 2D beam, and then I'll show you how to perform this analysis with the basketball hoop. And if you have some questions during the session, please ask, and I'll try to answer in direct or maybe at the end of the webinar. Okay, so first to begin, I like to define what is an optimization problem, because it's very important to understand what will follow. Optimization problem is composed of three things: an objective function, so this is the value you want to reduce or increase in the model, so the function that have to be optimized by the software. Then you have some constraint condition, which represent the design condition that must be satisfied always. And you have some design variables. So the variable is something that can change randomly, so this is what is defined during this optimization process. So I'll give you some concrete examples, of course, so you understand what I mean by that. So first of all, let's talk about adequate design. So this, when I consider this basketball hoop problem, for example, I have certain objective function, which is here to minimize the deflection, maybe under the dunk and the ball pressure loads. I have some constraints, which is to resist to the dunk, and to that, for example, the size of the board panel is fixed. So this is also a constraint. So I need to always, in my design, keep these things in head. And what I call adequate design means that this is the process to obtain my final design, but out of many solutions. And generally this design is made by experience and intuition. So if you already designed in your life a lot of basketball hoops, so you know, oh, the size should be something like that, then I put a bar here, and then I got design. So this will be the adequate design. Then what is the optimum design? So if you look at this, it's quite different. So in these many solutions that I was talking about, because design is all about choosing the right solution. So this is the one solution that either minimize or maximize the most crucial undesirable performance number in your model. So something you want to, so it's about the optimization, the function that I talked about. So you have to maximize this function or minimize it. And using the simulation. And finally, you consider some economical constraints, for example. So you want to reduce the material in the model. So you want to reduce the costs. And you want to have greater performance at the same time. So the only way to get that is to use some kind of tool that will tell you a way to reduce the mass at the same time to increase the strength, so to optimize the model. So you can see the difference, for example, between these two models is that, for example, the maximum deflection in the model on the left is 1.86 millimeter. So if I do the simulation and everything, and on the right it's 0.5 millimeters. So I minimized the deflection. Now, what is the optimum design driven process? Well, first of all, you have a formulation of a problem. So this is typically your design problem. You want to design a basketball hoop. Then you have the conventional design process, which is first to take the initial design. So then let's say you do your design modification. So by experience, intuition, you say it shouldn't be like that, it should be like that. Then you do some analysis to see if it checks the requirements you first gave. Then you do some other modifications. So you add some stand, you do again the analysis, you change maybe the size, you add some part here, and finally you get what I call the adequate design. So you see this conventional process comes from a long series of repetition, so the design always must be done again and again, and this is taking a lot of time because you really never finish to make the design like that. So design time takes approximately like that. Now let's check what is the optimization-driven design process. So first of all, the thing is that you have this initial design that you input in the computer, and the computer, using the topology optimization or maybe another type of optimization, will give you an optimized shape that you can consider in order to remodel your CAD and make a new model which is more suitable to your design and more optimized. So this is optimized block, and of course in the software at the same time you can do the analysis to check that it fits all the requirements. So, and here you get the optimum design. So the design time is a lot reduced in this case, and you get also better characteristics, better resistance of your model, and you decrease the mass, you decrease the cost as well. Now, there's a lot of possibility to optimize. It's not only one type of optimization. So you have 4 types actually of optimization that exists. The first is called the topology optimization, so the one I will talk about today. So in this topology optimization, what is optimized is the element shape density. So I'll talk about how it works right after. So actually the mesh size doesn't change, so it stays the same, and you get the new area based on the mesh density. Then the size optimization is a bit different. It's working by optimizing the properties that are assigned to your mesh elements. So if you have some beam elements, for example, in your model, or some plates, this size optimization can optimize the diameter of the beam, or the thickness of the plate. So you can see here. So you can imagine this is a beam modeled in 2D mesh. So size optimization will tell you what is the best thickness for this plate in this beam. So in this case, again, the mesh stays the same, and the only thing which changes is the property which is assigned to the mesh. Now you have also shape optimization. So in shape optimization, the geometry so it's based on geometry. So the location of some hole, for example, the size of the hole, all that can change. So this is based on, so the model will be remeshed in this case. And finally, you have the bead optimization. So bead optimization is a bit different. It's optimizing the thickness of a plate, for example, using what's called bead. So by determining the bead arrangement. So actually in midas NFX we support 2 types of optimization. The first one, the topology optimization, and the second one, the size optimization. we don't support yet the shape and the bead optimization. Now, in this part, we'll talk about the topology optimization a bit more in detail, because it's the topic of today's webinar. So, the topology optimization is the optimization of the layout, so which determine the most appropriate distribution of material. So just let's say the weight of the model. So it's a way to optimize the density of material that is used in the model, and it's particularly useful to optimize the mass of your part, for example. So density method is always used, and design variable is fixed as the element density. So as you can see in the process here, you have first some kind of topology optimization here. So you can see the model it gives you a final shape like that. Then the CAD is modified to take account of this shape. And then a second topology optimization is done in order to get the final model. So the topology optimization is used more in the conceptual design stage. So because it's when you have the essential evidence that you need for your design, it will provide you some alternative idea that you can consider to include in your design. So it's not you shouldn't think that it will give you the final shape and then you can go on and produce it. It's not working like that. It's just a way to give you some idea of the way you can improve your design. So as I talked here, you have an initial guess. So this is the initial design, let's say, that you're considering. Then you model it in finite element, in midas NFX. You apply the load. And then in the optimization analysis, a sensitivity analysis is performed, and then your model is updated according to the mesh density. Then you have some kind of check which check the error and if the criterion you defined are satisfied or not. If no, then this is done again and again until you get some better shape than that. And then if it's satisfied finally, then it plots the results. So this is the topology optimized shape. So we'll do a similar example right after. Now in the topology optimization design problem that you can consider, it's not only about linear static, but you can also optimize some dynamic properties like the eigenvalues or the frequency response. So if you have, for example, let's say a robot arm or something like that, and you want to be sure that in some dynamic condition it will sustain the vibration, and you want to optimize your model in such condition, then you can use also topology optimization. So you have two types of analysis. You have several types, I mean. You have the minimization of static compliance. So this is the objective function. And in this case, the design constraint is the volume ratio. So you decide what will be the final volume ratio that you are targeting. And then this is the analysis which is used, linear static. And finally, you can also input some manufacturing condition. So you have dynamic compliance that can be also an objective function if you want to do it for frequency response analysis. In this case, the design constraint is also the volume ratio. And you can also minimize the volume ratio. So in this case, this is the objective function. And what the design constraint is the displacement. So in this case, it's a bit different. In this case, you have the possibility to put a sensor somewhere on your model to test the value of the displacement, the maximum displacement at this sensor during the optimization process. and as soon as your design constraints is satisfied, then it will give you the minimized volume ratio. And you can also do it for the model analysis, so to maximize the average eigenvalue. So let's talk briefly about the density method, which is the method used for this topology optimization. So I'll try to explain that in a simple way. So at the beginning, the initial design that you have is a design where the density ratio of all the mesh is 1. So all the mesh are set as 1. But during the optimization process, in function of the boundary condition, the loads, and all the constraint that you defined, the optimization will affect some kind of coefficient to the mesh. So it will say this mesh is necessary in my analysis, so it will stay equal to 1 for the mesh density ratio. But in some area, I don't really need to have this mesh in my analysis, so in this case, it will be set to 0. So the volume ratio is proportional to the shape density. So if the shape density decrease, the volume ratio will decrease in the same way. But the stiffness ratio is not exactly proportional. So, for example, if you decrease to 0.8 the average shape density of your model, so you suppress some parts and then it begins 0.8, you see that the stiffness ratio begins around 0.5. Okay. Now, let's talk briefly about the analysis procedure. So this is the procedure to make the analysis in midas NFX. So it's almost the same procedure than when you're doing linear static, for example. So first you define the linear static frequency response analysis. So you have to define your model for this. Then you define, of course, the property, the material, you create the mesh. Then you have to define the boundary condition and the loads. And then you have to choose between the minimum compliance, so to minimize the compliance or minimize the volume. So if you minimize the compliance, you have to set the volume ratio as the design constraint. So you have to choose what is the maximum volume ratio that I want to have. And then if you minimize the volume, then what you will set is the stress and displacement. So you set the sensor and you tell the software that I want a minimum displacement which should be below 0.01 millimeter, for example. Then you can set some manufacturing condition, you analyze case, and then you can analyze and get the result. And on the right is the process for maximizing the eigenvalue. Let's talk briefly about the checkerboard. It's not very important, but I'm still explaining because it's some parameter that you can play with it in the optimization analysis control. So when you are doing topology optimization, let's say the mesh density is changed in your model. So you have some mesh which are set to 1, some mesh which are set to 0, but it cannot be only 1 or 0. You have to be, you also need to have some mesh which are set to 0.2, 0.3, 0.8. So it's not all black or white, so you have some gray part inside the two. So this checkerboard method will let you choose, do you want really to have black and white, or do you want also to have this value, intermediate value between the two? So it will depend, it will change slightly the shape of the model. So if the checkerboard option is set to low, for example, then you'll have something like that, but the manufacturing method will be more complex, but it will correspond more to the theoretical result. If your checkerboard is set to high, then it will be much more simpler to manufacture the parts, but at the same time it will not really correspond to the theoretical value. Okay. Now let's talk about the design set and the non-design set. It's also something that you can set if you're doing this topology optimization. When you have a model, there's always some part of the model that you cannot change. So this is a constraint of the design. So in this case, this is what I call a non-design set, because you cannot design this part, so you set it as a non-design set. So it's really simple. So in this basketball hoop example, this board is set as the non-design set domain. So you see that it doesn't change after the optimization. If you have some 1D, so 2D or 1D element or maybe rigid link in your model, this will be automatically set as a non-design set because it cannot change the mesh density. Now, the last theoretical part, let's say, is about the manufacturing condition. So sometimes when you do this topology optimization, you get something which is difficult to manufacture because it's, let's say, more abstract conceptual design than something that you can directly go to the factory and say, I want to produce that. So in order to give you something a bit more realistic, you have the possibility to add some manufacturing conditions. So you have two main type of condition. One is the casting direction. So you can view the beam, for example. If you don't apply this casting direction, it will give you something like that with a lot of holes inside. So of course you cannot produce something like that. So you just tell it, I want a casting direction in this direction, and it will give you something much more like a beam. Then the repeat condition, also called symmetry, is when you have a symmetry condition which is required in your design. So in this case, you can also set it as a manufacturer condition. Okay, now let's go to the first simple tutorial to show you how it works and how you can use this wonderful topology optimization to work on your design. So we'll do first a very simple example in 2D, which is the 2D beam topology optimization. So it's a typical beam like that. It can be a bridge, for example, and you have to fix it in one direction, and then here you put a load position. So the volume reduction that I will target is 45%, so I want to reduce the volume of this design area by 55%. So we don't know what is the design optimal shape, let's say, so let's check what the software will tell you. So this is the actual model I will consider. So I will fix the model here with boundary condition. I will put fix the y direction here and put a load of minus 50 Newton in y direction, and then afterwards I'll put also symmetry here. Okay, let's go into midas NFX and check how we can get such result. So first of all, check that you are in the analysis mode. Okay, it's a 2D problem, so I check 2D. So to check if you're analysis mode, you go before you open the project, you go and click on application here, and you change to analysis mode. Okay, now I got my area that I want to design. So first thing, I'll create a rectangle. Here, that will be the shape for my beam. Okay, I'll check the make face option, so it will directly create the face like that. So it's not really the same dimension that in the tutorial I mentioned, but it's only for the purpose of the demonstration. Okay, now I have a surface which will represent my beam. So the first thing I'll do is I will decrease a bit the grid size. So I'll put it, let's say, to 5 millimeter. Okay. Okay, like that. Okay, and I have to add some material, so I will use just the default material, which is the alloy steel. I will not change that. I will add some 2D property, and the 2D property will be a plate which will be defined with 1 millimeter of thickness. Okay, now let's just mesh this. So I will use the map face to mesh this with a hexa element, and I will use a size of 1 millimeter. Oh, it's a bit too small. Let's say 2. Okay, 2 seems okay. Now that I did that, I will assign the boundary condition. So let's choose the constraint, go into the advanced tab, and we'll put a constraint in x direction to the nodes which are here. Apply. Then set some ty condition on this node here, and I will apply my force on the node on the right. So it will be in y direction, and I said minus 50, I could put also minus 100. Okay. Okay. So this is the finite element model, and now we're ready to generate the optimization case. So for that, go into Optimize and choose Topology Optimization. So I'll give you a name, vBeam. Here you have the choice between linear model or direct frequency or model frequency response. So here I will choose linear static. I will choose the minimum compliance method that I talked about. Here in this area you have the design set and the non-design set. So in this case, the mesh set that I created is here. It will be all design, so all in the design set. Now let's go in the analysis control and check the option for the optimization. So first of all, the checkerboard reduction, so I will leave it to medium. The objective function norm, which is so this is the convergence criteria that it should verify. And you have also a second convergence criteria on the design variable. So here it's the volume ratio. No, sorry, the minimum compliance. Yeah. So, and here you have the target volume that I want. So my target volume is 45%. So I will enter here 45%. Click on OK, and I'm ready to run this optimization. So now you have the optimization, the objective function, which is here, and the iteration. So this is an iterative method. So you see that it's converging, and finally you get the result. So in 12 seconds I got my optimized result. And here you see that you have the material density. So the first step it's like that. And when you increase your analysis, you see that the shape of the beam is changing until you reach the final optimized shape. And at the end you have you can verify the linear static analysis to view the result on the final shape. So when you got this result, you can update your model. So click on Topology Optimization. You can choose the step that you want to optimize. So it can be this one, for example, or the last one. So at the same time, you remember that I checked medium for the checkerboard. So this is why you have still some part like that in gray, let's say, between the parts. Okay, now I choose just the last step, and I can play on the material density. So you can see here, if I choose a material density of 0.45, which is what I wanted, and I calculate, I get a reduction of the volume of 45%. So when I got that, I can remesh the model, choose, let's say, 1 millimeter for the remesh size, click on OK, and NFX will directly generate for you the remeshed model. So now you have the optimized remeshed model that you can, let's say, export it in STL format in your CAD, and you can remake a design based on it. Okay, so now that I got that, the thing is that I want to apply also some kind of manufacturing condition on that, because this is not a shape that is easy to manufacture. So I come back to the pre-mode, and I will define the symmetry condition. So to define the symmetry, I have to go here in the walk tree, coordinate system, and add a new coordinate system. So I'll choose a name, symmetry in Y direction, and I have to choose the origin first. So origin will be here in the middle of the beam. The point on the Z-axis, so it should be like that. Okay, sorry, like that. Yep. So this is 0, 50, and 1. And this is 1, 50, and 0. I can preview. Okay, looks good. So this is my new coordinate system that I'll use to assign the symmetry. So I just copy the analysis case that I made previously. I edit it. I go in the analysis control, and here you have a tab called manufacturing condition. So here I activate this symmetry condition, the planar symmetry, and just okay, and then I put the reference system in Y direction. And this is the symmetry plane. Okay, now I printed that, and I can run again the analysis. Is there something? Is there something? Is it still okay? Are you still following the presentation? If there is some question or some problems, please don't hesitate to ask. Okay, so I got my all the results, so I'll check it. And you see that the new optimized shape is like that. So much better, let's say. So as I was saying, this is much better to be manufactured as it's symmetric. Okay, so that's all for this simple example, and now we'll go on for the basketball hoop example. So, and I'll show you step by step also how to do topology optimization on this basketball hoop model. Let's go back in NFX. Okay, I'll close the actual models. Okay. Okay, again, check that you're in the analysis mode. Open a new project. So this time it's a 3D project. I'll use millimeter unit. Okay. Now this time I will import a CAD model that I defined previously. So this is a parasolid format, but you have all the formats also available. Okay. So this is the, let's say, the conceptual design of my first basketball hoop. So I'll use that to optimize the shape and get my final result. So the first step is to assign the material and the properties. So let's go here. So I will do something. Instead of creating all the properties and the material, I will directly import them from a previous model that I made, so I don't lose some time. So I have two properties, the frame and the backboard properties, and they are both assigned to two materials. The frame is an alloy steel material and the backboard will be an acrylic material. Okay. Now that I did that, I will mesh this model. So I'll go into mesh, 3D mesh. Again, this is very rectangular shape, so I'll use map solid. The size will be 75. So I will use first the frame property, and I can preview the size. So it's size will be like that, so it looks okay. Let's go in the advanced property. Okay, it will be first order element, apply. Okay, now I got my meshed model. Now what I will do is I need to separate this model to create the non-design set. So I will go in the walkthrough here and I will create a new mesh set. So I will give it a name, so it will correspond to the backboard. Okay, and you right click on it and include, exclude element and node. So do that, then I change the view to view it like that, and I will select the element that I want to put in this new mesh set. So now you see the mesh have been separated. I have one mesh set to correspond to the backboard and one mesh set corresponds to the design of the frame area. What I need to do is to assign the backboard property to the backboard, because for the moment it's still the frame property which is assigned. So I'll go into the mesh element parameter 3D and change property. So here I choose the mesh set, backboard, I choose the backboard property, I click apply. I will do the same for the other mesh set to be sure that the right property is assigned. Okay. Okay. Now if you click on the mesh set and you look in this window here, you'll see which property and which material is assigned, and you will see also the mass and the mass center, so you can view these results here. And in the case you want to check the mass of this model, it's possible using the measure tool here. So here you can choose, for example, this mesh set, calculate, and it will give you what is the actual mass of this model. So it's very heavy because it's a full big block of steel. So of course I'll need to optimize that. Okay. Now the model is not finished because I don't have the hoop here. So to model the hoop, instead of modeling it in 3D, because it's not really required in this analysis, I will simply create a node and create some rigid links in order to simulate that this is the hoop, and I will assign the load to it. So first of all, I'll create a node. So I'll just go in the node tab and create a node manually. So I just select the point here, and my node is automatically created. So you can view it here, manual node. When you have this mesh set in here, it means that have been created. And go in the element and create, order tab, rigid body, and now I have to select on my model the points I want to connect with this node. So I select like that. Okay, so now I selected only the point here, and I need to set the master node as the node I just created. and I click on OK, and now I generated my rigid link with this node. Okay, now the model is ready to apply the boundary condition. So first, let's apply the boundary condition, the constraint. So on this face here, I just fix the nodes. So this is the first boundary condition. Second, apply the forces and the loads. So the force. So the first force type which is considered is the dunk. So if you have a basketball player, you can think that he's dunking, so he's grabbing the hoop, and then you want to be sure that the basketball hoop will resist. So I apply my load here, and I will say it's approximately the load of a human being, so minus 2000 Newton, and give its name to the load set, call it dunk. Okay. Now the second type of load is pressure on the board, because you can imagine it's receive a lot of pressure because the ball always touches the board. So it will be pressure. So this pressure will be assigned on this face, and it should be in y direction. Y direction, and the value of the force is 0.000711. Okay. And let's give a name and call it ball pressure for this new load. Okay, got it. So now my model is ready, and the only thing I need to do is to define the optimization variable and constraints, and also the function that I will use. Just a last advice between going on. Be sure that the non-design set and the design set are linked together. So it can be the nodes are connected, or it can be a contact between the two. Because it happens that you create your model and you forget to assign a contact between the two parts. So in this case, you'll have some error. So, okay. So in this case, it should be connected, because, but I can check. So if you want to check that it's connected or not, you can go in the Mesh tab, check the mesh topology, and here should three faces check. So click on apply. And now if you see that there are some strange face inside the model, so it means you have some free surface inside, so it means the nodes are not connected. So in this case you'll need to change something. So here in this case it's okay, so I don't need to do anything. Okay, go on. Now let's create my optimization case again. Topology optimization. So what I will minimize is the compliance. So linear static, minimum compliance, and let's choose the analysis. Oh, no, before doing that, you see that I have two types of load. So if you do like that, you assign the dunk and the ball pressure, it will consider the two loads at the same time. So if you have a basketball player which is dunking and at the same time you have the ball, so you can imagine it's not possible. So what you need to do is create a second subcase. So you give a name to that, ball pressure. The first subcase will be dunk. But to change the name you have to press F2 if you don't know. Click on this button to assign all the condition to the two subcase, and then here I will drag and drop the ball pressure and drag and drop the dunk. So you see I have two cases. The first case is if I have a dunk, and the second case if I have a ball pressure. So in this case the optimization analysis will take account of the two types of load, but separately, not at the same time. Okay, now it's time to put the analysis control parameters. So checkerboard reduction, let's leave it to medium. objective function, okay, I will keep that. Design variable, I could check it. So of course, if you check a second check of the convergence criteria on the design variable, the results you will obtain will be more accurate, will be more fitting to your design criteria, but it will take much more time also. So you have to think about that. Okay, the target volume is 4%. So I want to get volume which is equal to 4% of this. Click on OK, click on OK, and I can launch the analysis. Okay, I'll give it another name, because I see this name is already taken. Okay, now you see it begins to optimize the objective function, and it's converging quite fast actually. So we'll wait a bit. So instead of just waiting for the final solution, I will open a model which I already calculated to show you directly the result and to go a bit faster. So here it is. Okay, so this is exactly the same model, and here you see that in the same way you have maximization of the material, the mesh density, and you get something optimized like that. So if I want to visualize, I can use the ISO surface, for example, like that. Okay. Okay, so you get something like that for the optimized shape. Now, if I want to generate the my model, same way, I go in Topology Optimization tool, then I choose the case I want to consider for the optimization, so I can use the last of them, for example. Then choose the material density. So don't forget that this material density will play a lot on the stiffness. Calculate. So you see that here I get 89% of volume reduction. And now to get the FEM model, you can just input the mesh size. So you have two choices. The first one is to create directly the FEM model in 3D mesh. The second is to generate only surface mesh. And you have option also to export in STL format directly. So I'll choose to merge the nodes. Okay, I'll change the name. Okay. So now again it will remesh the model to optimize the shape. So this is the optimized shape that I get. So of course the results you obtain at the end depends on the parameters you used, so design criteria, the type of the objective function, so you have a lot of parameters to play with, and it will give you some results slightly different in function of the parameters you are really optimizing. So in this case, okay, I want to do the analysis again to check the final result. So I'll check the boundary condition. So okay, my constraint is still here. Let's check that the mesh sets are merged together. So I'll check the free face. And you see that in this case you have some phase between the two. So it means these two mesh sets are not merged together. So in order to get that, I will simply assign an automatic contact between the two mesh sets. So it's very fast, and you can check here that this contact has been assigned. Okay, and now I can go on and edit. Don't forget to to update, let's say, the results. So the dunk, okay, take off the dunk, take off the dunk here, and here I have to put the bulk pressure for the first, it's the other, sorry. Here's the dunk, and here the bulk pressure, okay. My contact, check that the contact that I just created is assigned in the two cases. This is important. And analysis control, here I have nothing to change, so leave it like that. Click on OK, and so this is linear static, it's not optimization. Okay, and then I got the result. So this is the final result, final displacement for the dunk. So you have 0.02 maximum displacement, and maximum displacement in case of the bulk pressure. So it's 0.009. So it has been really optimized a lot. This is the stress inside the model. And of course, you have to check also the safety factor. So here the safety factor is really has no problem. It's much greater than 1. So you can use this shape. Okay, so it's all for this demonstration about this. So now it's almost over. So I'll show you how to get more training material. So if you want, let's say, to train on this model or to get new tutorials to try, you can follow the procedure. So you can go on midas NFX.com, and on Learn and Support section you will find the tutorials. So we have a lot of tutorials. I just added some tutorials about topology optimization, so the bicycle crank, for example, if you want to try. Then if you want to join other and next webinars that we will do, you can go in the e-learning section, and the next webinar will be about CFD analysis, fluid dynamics. So it will be on the 7th of May, so in 2 weeks, on Wednesday. So you are invited, and you can go on the website to register for this webinar if you're interested by fluid dynamics as well. Now, if you don't have NFX yet, or if you are not client of Midas, you can download the NFX trial to test the software. So you can test it for free for 30 days, which is a full functional version. So you can use topology optimization in it. You can as well use CFD or any type of analysis. So thank you very much for attending this webinar. I hope it was useful, and you learn a lot of things about the design and optimization of parts. And I hope you'll join the next webinars, and also join us on social networks if you are on it. We are on YouTube, on Facebook, on LinkedIn, on Twitter, and Google+. So if you want to discuss with us, you can join on these networks. Okay, and now I'll take questions. So if you have some questions, please ask right now, and I will just answer in direct. Don't hesitate. You can ask any question about the software, about optimization, about anything you're wondering. Okay, I have one question about how I can apply the sensor to check the displacement during the optimization. Okay, so I'll show you quickly how to do that. So this is the second type of optimization that is called minimize the volume ratio. So in this type of analysis, I go back on my first design, and here you go in the analysis tab, and you see you have a tab called sensor. So if you check the sensor, you can select one node, for example, in the model, and check the condition that you want to check. So it can be displacement, velocity, temperature, something. So here I'll check displacement, total translation, and you can check if I want to check the sum, the maximum value. You click on OK to create the sensor on this position. Then when you create the topology optimization case, you have to choose minimum volume, and you see that in this case you have to go in the subcase control, check displacement, and here it asks you where is the sensor, so you just check the sensor you have to define, and that the displacement value you are targeting is less than, let's say, 0.03 for this subcase. So you define it like that, you click OK, and now you can do the same that I did previously. So it will be slightly different because you are optimizing in function of the maximum displacement. I have one question about how this tool is different from ANSYS FEM. Well, it depends on what you want to do, because midas NFX is similar in some ways because it's very general software for mechanical analysis, but there's also some difference, and in function of your workflow, in function of what you want to get, it will be more maybe convenient to use NFX. For example, NFX is fully integrated in one unique environment, so it's something that you can consider if you are a consultant, for example, and you need to do a wide range of analysis going from linear static to dynamic to nonlinear explicit to CFD, and NFX provide all that in one unique environment. So you can do the same model and perform all this analysis on one unique model. You don't need to do remodeling, you don't need to do that. So it's very convenient. After that, we have also two interfaces, designer mode and analyst mode. So in function of if you're a designer or an analyst, you can use the workflow that is better for you. And in general, you can say NFX is much more easy to use than ANSYS because the workflow is much more simple and straightforward. And we provide also a lot of tutorials which are really easy to follow, and you'll be ready to work on your model in maybe 1 week or 2 weeks, depending on what type of analysis you're performing. I hope it answers your question. So is there other questions? Okay, I see I don't have any more questions. So I hope you enjoyed the webinar, and I hope it was interesting. And if you're interested in the next webinar we are doing, please go on our website and join the next CFD analysis webinar. And you can also, so I will share this webinar video on YouTube, so if you want to look it back again, you can, I will send you the recording later on. Okay, thank you very much, and goodbye, and I hope to see you next time.